Okay, good evening, everyone. This is Ken Coleswell. I'm the chair of IEEE Iowa Illinois section, and thank you for joining our presentation here on machine safety and functional safety. And I introduce Matt Henning from Van Meter, who's a safety expert that is going to give us a presentation on machine guarding. So take it away. And if you have any questions, if you want to just do a raise hand and I can unmute you, we can just talk right then.
Hey, thank you everybody for coming. My name is Matt Henning. Work for Van Meter. I'm what they call a smart devices specialist. So I handle everything from push buttons, terminal blocks. Oh, what else? All industrial control. I do safety, sensing, connectivity, and I also handle pneumatics. So I'm a TUV functional safety engineer. I've had that going on 6 years now. And so I spend a lot of time in the safety space with just machinery. So again, this is keeping people safe from machines that they have to operate around and interact with. My background, I started with Squarity Company way back when I hadn't even graduated college, and they hired me, and I've been in the industry for 30 years now, 30 plus. A lot of experience, worked with all different aspects of industrial contracting, engineering consulting, and now, like I said, the last I'd say probably 10 years has been very dedicated to machine safety. That's really evolved over the years. Back when I started, we ran one wire to an e-stop and that went to a master control relay and you hit the button, it fell out, or maybe it didn't. We didn't know. We never thought about what happened if it didn't work. We just assumed it always would. So machine safety is kind of a different way of looking at keeping people safe when they have to interact with machines. There we go. So when we talk about machine safety, this is kind of a thing that we go by, the machine safety life cycle. And you notice it's a circle, and there's a reason for that. A lot of people think safety is I design it and I build it and I put it out there and I'm done. And when it comes to machine safety, that's not really true because we do things to machines and we change things and we speed things up and slow them down and we move a process or we change a little thing here. Maybe the operator has to do a new operation or a new task. So anything like that, any event that happens, you have to start that cycle over again. So the idea between the machine safety life cycle is to continuously look at that machine, review it, try to improve it, verify that it is the way we thought it was and that it's doing what it's supposed to do, so that we have good confidence that no one's going to get hurt and we're not going to impact productivity. So can I go through it? It's a step process. So obviously, if you have a machine and someone has to interact with it, we call that a task. And so we do a risk assessment. And the risk assessment is basically you have to first identify all the tasks that someone does with that machine. And that could be an operator, it can be maintenance and repair, it could be simple people that are around it. I always notice when I go to plants, they have yellow lines, and they tell me to stay between them because I don't know what I'm doing there with that facility because I'm not part of their, not part of the workforce. But sometimes people go outside of those yellow lines. So there again, you have to think about that risk. If someone steps out of the box and they walk into this machine, they don't know anything about it. Could they get hurt? So that task hazard pair relationship is honestly probably the hardest thing to do. People are always afraid of risk assessments. Like, well, how do I assess the risk to know how bad it's going to be? That honestly isn't that hard. And we'll get to that later where I show you the easy way to assess risk so that you can determine, what performance level you want to build to. So that's kind of step one. Then we go into this. Now we know what all these tasks are and the hazards. So we do a safety functional spec. So someone has to then write out when the operator does this, here's how we're going to keep him safe. And it's kind of a wordy document. You lay everything out. The operator picks up this tool and he goes to this position and he does this. And so you really define it out what is happening. Next step would be safety system design. So somebody then has to sit down, typically controls engineers, mechanical engineers, people like that. They're going to look at that and they're going to come up with these solutions to how do we protect someone in these situations. And then the next step safety system installation and validation. After we've done that, somebody has to put it in. So you have to have someone qualified who understands the design, who understands the basic machine safety. They're going to install it properly, and then they're going to validate it. So they're going to test it to make sure that it does what we thought it was going to do. If we get past all that, we get to move on to maintenance and improvement. This is the step I think a lot of people forget about. But again, code, when we go through those, the standards tell you that an e-stop should be exercised every month. If you have an e-stop, it's a mechanical device. You want to know it works. You want to hit that e-stop. You want to make sure that it did what you thought it would do, because now you know, okay, we're still safe. So testing, continuous testing of your things. If you have a light curtain, should be part of a maintenance cycle. Put your hand through that light curtain to shut the machine off. You know, if it doesn't do it, then you know we have a problem. The other design would be improvement too. Are there newer technologies? Did we change our process where we can maybe eliminate the person interacting with the machine, replace them with a robot, something like that? So that's where you want to think of this as like a wheel. It's continuously rolling. You're going to do this over and over again and always. And the steps are kind of tied together. So you do your risk assessment. That's going to tell you a performance level or how safe do we need to be. That's kind of tied to that safety system design and verification. Your designers can't design the safety system until you've done a risk assessment to know what you have to design to. And then we get to that safety functional spec. Again, your validation, you can't do a validation if you don't know what you're validating. So you have to validate to that design requirement spec. Safety standards, they've been out there a long time. There's tons of them. We have American standards, there's Canadian standards, there's European, there's Chinese. So I get that question a lot. Which one do I use? I've got my favorites. That's really up to your facility and your team and what you think is the one you want to use. In America, obviously, we're driven by OSHA. So we're kind of backwards here as far as safety goes. In Europe, the OEM that builds a machine is responsible for making it safe. To me, that makes sense. I'm an engineer. I designed a machine. I really understand how it works. I'm probably the best person to figure out how to make that safe. In America, we wrote our code kind of backwards. We just said the end user who owns the machine has to make it safe for their employees. So here now you have a person who isn't the expert on that machine, but they're responsible for making it safe. I wish they would change that code, change the law. It's been in there a long time that way, but I don't think that's going to change. The nice thing is the attitudes towards machine safety have changed in our country, and most OEMs and machine builders and things like that, they ship all over the world. They have to do this anyway, so it's just kind of applying to us here. So it's kind of nice in that regard. But like I said, a lot of standards out there. You have A, B, and C types. A types are very broad. It's the big book. It's the whole book of everything, like ANSI B11. B types go into a specific action or type of behavior. So again, B11.19 would be our machine guarding, and it gets more specific. And then you move out to C types, and C types are a thing. So it's a conveyor, it's a robot, it's a power press, hydraulic press. The nice thing about the C standards, there's a standard for just about anything you can think you're going to need to do in your factory. So they get very specific. The beautiful thing about standards, I always tell people, they're a huge layer of armor against hurting someone and also litigation. So if you have an incident and you have, worst case scenario, have to go to court, they're going to ask you why you did this way. Why did you design the machine this way? Why did you put this safety device in there? Why, what was the maintenance procedure? All these things. If you say, well, we had a conveyor, so we used ANSI B20.1 and ANSI B11.19 for machine safeguarding, and that's how we did our things. Like I said again, it's that layer of armor. It protects you because now you have the standard in front of you protecting you, that a bunch of people have got together, come up with a general consensus. This is the way to do it. And they review that constantly. It's being updated and modernized. So now you don't have to explain every little thing you did. You literally can say, we just did it the way the standard told us to do it. So I highly recommend to people that don't have standards, pick one, get a team of people together, hash through them, ask people like me what I think you should be using. other people in the industry that have a lot of experience with them, but definitely have one. I'd highly recommend it. So in our side of the world, we typically use ANSI standards. The other side is the ISO IEC. And there used to be there are a lot of differences, and that's what got confusing. Well, I build the machine here to this standard. Can I ship it to Europe, or you build it over there? Does it work here? So about 10, 15 years ago, all these different groups of people got together and they started doing what they called a harmonization of the standards. So they're all trying to get to the same point, right? So we start at the same point, we have a dangerous machine. We end at the same point, we want to have a safe machine. We may take a different road than them to get there. Slight differences, but again, the beginning and the end are the same. So through the harmonization, it really doesn't matter as much anymore. If you use ANSI B11.19 and you read all the specs and calculations and how they do things, it is so close to ISO 13849 that you wouldn't know the difference. It really, they say that they end up saying the same thing. So it's kind of nice that way. So again, it's not like, oh, I picked the wrong standard. It's just have a standard and design to that standard. So why do we even have machine safety? Why is it a thing? So, OSHA defined if you have a machine, you can't have people buy it, lock it out, tag it out. That's originally how we did it. So if you had to work on a machine, you had to shut it down. If you had to do basic maintenance, shut it down. If the machine had a jam, shut it down. People have to add parts to the machine, lock it out, tag it out, de-energize and test. As machines became more complicated and interconnected in factories and they were more automated, that became virtually impossible to do. It just had too big of an impact on manufacturing. So they got together and they came up with they call what we know as machine safety as alternative measures or alternative means. So basically it says, okay, you always lock out and tag out unless you meet these conditions. So when do we not have to do it? It's called the minor servicing exception. So they defined it. If you have a task to do, you have a machine that puts lids on tubs. So the operator every once in a while has to load lids and tubs into the machine. So the task has to be routine. So it's performed on a regular, basis, and it's just part of what the machine does. It's integral to that. It's repetitive. I don't do it, they consider repetitive once an hour. So that's repetitive. If you're doing it 20 times an hour, it's definitely repetitive. So part of your production cycle requires this action to be done. And again, integral, it's part of the function of the machine. It's how it has to be done. So if you can meet all these, answer these questions, then yes, okay, now you can accept yourself from lockout tagout and move on to alternative measures. How do I do that? Again, standards. ANSI Z244.1 tells you exactly how to do alternative measures. So if anyone's ever familiar with, you had lockout tagout, but then you could get a live work permit. So you could, under circumstances, do work live, but obviously there's a huge criteria. So, and you had to fill out this big sheet of information with all the details of why you couldn't shut it down and what would the impact be and how are you going to, guarantee people are safe. They've done the same thing here for the alternative means. So in the standards, it actually has charts. You fill them out, answer the questions, and then it says, okay, you're good to go. I have had people, they ask, do I really need to do that? Can I short circuit it? I always go back to the suit of armor. You want an armor, you want your shield, and you want your spear. So this is just another one of those tools to help protect you. Yeah, do it, fill it out, put it in the file, because if anything happens, it's nice to have that done, and it shows you put the thought into it and you did your best to do it the right way. So I would highly recommend always doing that. This is just an example here, so you can kind of see task data. So you have to identify, person's doing this, their tool changes, cleaning, whatever. So you define it, how often it's going to be. That's a big thing. Again, what are the impacts if we lock it out? It's going to interrupt service. It does this. There's something in the process that can't wait for the time to shut down and start back up. Then you kind of put in there, are there things we can do to negate the person being in there? No, we have to have a person there. So we move on. So again, this seems simplistic. A lot of people don't like doing it, but I'd highly recommend having this written out because again, as more people get involved in the project, everyone's on the same page and understanding what we're trying to achieve. Biggest question we always get, oh, well, that machine's old. It's grandfathered in. In the world of safety, the codes all say every year you have to review every machine you have and make sure that you have to revalidate it. You have to make sure that it's still doing and operating the way we thought it would. Nothing's changed. So that takes the grandfathering right out, because any machine that's a year old is supposed to be assessed, evaluated, and revalidated. So again, in the standards, it kind of tells you, are you doing a minor repair to a machine? It doesn't change the safety function, then you don't have to do a risk assessment. You just test everything to make sure it still works. You're putting something in, you're changing some component of the safety system. Well, now you have to do a risk assessment again to make sure you didn't change anything and retest it. Major reconfiguring, you're rebuilding a 60-year-old machine for sure. Then, okay, now you really have to do that risk assessment. You have to go through that whole safety cycle again. So again, it kind of will help you make these decisions as to what's our responsibility when we have these older machinery. Even, I get too, people are like, well, it was fine here. We moved it to a different plant, so we don't have to do it because we didn't change anything on the machine. But your plant's a new environment. So maybe, a big part of safety is if there is an incident, can the person get away from it? Well, if it used to be in the middle of the room, but now it's next to a wall in a corner, they may not be able to get away from it. So again, you have to do that risk assessment again to determine what that environmental factor is going to have on safety. A little more detailed thing here you can go through. Again, this is why I like the standards, ANSI 11. You go in there, all this, you don't have to create this information. It's all out there. You can find it and then just like I said, do what it tells you to do, conform to it. Risk assessments. People hate doing risk assessments, and I don't know why, because they're really fairly easy. We'll go through different ways to do it based on codes. Again, I have my favorite. You see the guy in that right top corner. I love that one. That's probably my favorite way to do risk assessments. It's pretty straightforward and easy, but you can use one out of the standards. You can literally, we have people that make up their own risk assessments, how they do it, which is fine. Again, you're just taking that liability on yourself. But you do have to do a risk assessment. And it does say that in the standards. It's not, there's shall and should. It's not a should, it's a shall. It's a shall and must. So it's required if you have a new machine that you're going to get around lockout, tagout, you must do a risk assessment. Again, nicely defined. We go through B11, you start there, it's going to come down. Now we assessed it, we did our risk assessment, now we got to reduce it. Now we kick over B1119. Again, tells you how to go through your design, answer these questions. Well, it's not safe by design. It's not inside a steel box with no holes that we can get in. So it has access. People can get in there and get hurt. We got to move down. And that's where, again, now you kick over from, engineering controls and functions. We'll move into ISO 13849, a specific C standard that's B and C standards are going to tell you how exactly to do it. And there is a hierarchy in safety. So obviously, anything as simple as we're going to put a sticker on it that says don't put your hand in there, which is obviously the least effective, up until we're going to put it completely guarded. There will be zero access for a human to get in there, which protects people from getting in there. Maintenance doesn't like it. So there again, it's kind of extremes. The big art form of machine safety is making sure that you make the machine as safe as you possibly can, but it doesn't impact what the operators do or how maintenance interacts with it, and it doesn't affect production. If the operator thinks it slows them down, maintenance hates it, and your production manager is mad because he thinks he's getting less product, they'll try to figure out ways to get around it. You want it to be seamless and integral in the background. The best case scenario is the only time your safety system is noticed or functions is when they're testing it. Once a month you go and you test all your devices. That means nothing happened and you were protected. That's great. And if it's that transparent and nobody knows it's there, they'll leave it alone and your production won't be impacted. Which standard should I use? Again, it's a tough one. There's a lot of good ones out there. I would say, again, if you don't have anyone that is into this at your facility, just reach out to people, like in my industry, Rockwell. Rockwell is a bunch of people we do. Most manufacturers do that can kind of help guide you through that. So the other trick here is, what is risk? So risk is subjective. It's not a for sure definite thing. So again, risk to me might be totally different than risk to you. So when you go to do a risk assessment, I always tell people you have to have a team. You don't have one person do it. You want an operator, you want a guy in maintenance, you want a controls engineer, you want a mechanical engineer, you want a production manager, you want maybe a plant manager, you want EH&S personnel on this. really you want a bunch of opinions because one person isn't going to see every risk on that machine. They're not going to even know, the controls engineer might have a good familiar what he thinks the operator does, but he's usually not out on the floor to see what the operator really does. So the operator may say, but I do this and this, and nobody knew. So again, you want to have a team building risk assessment. And I always advise people to have an odd number of people because it's consensus. So you don't want a even number of people. You want 3 and 3, and then you butt heads about you can't break a tie. You want to have 7 people or 5 people. That way you get to an answer, and then everyone gets on board and you move forward with it. So again, risk. My standard. I heard this a long time ago from a guy. He said, I look at a machine and the task that's being done, and I have daughters. So he says, picture your daughter operating that machine or doing maintenance on that machine, and then you determine what level of risk you're comfortable with. I kind of like that because it personalizes it, and that's the way you need to think about safety. Safety isn't just because we want to make stuff and we don't want to hurt people. Safety is a culture, and I've unfortunately had to go to facilities that have had accidents. I've been at 3 facilities where people were killed, and I got to tell you, it fundamentally changes the culture of that facility. It has a huge impact, well beyond the monetary impact, and it lasts for years. Everything, the main perception is, people feel bad. I could have prevented it. What did I do wrong? Up until, well, management doesn't care that they killed a guy. They're all about the money. I've heard all the things. So again, that's how I tend to look at it. I look at because I've been doing this a long time, and like I go to change a light switch, I don't shut off the breaker, right? I'll tap the wires to see if they're hot. Not the smartest thing. I know better, but I've done it a lot. I don't want my daughters doing that. So I for sure am gonna go tell them, no, you lock that breaker out, you wear gloves, you test it. It's a different thing. So that's how you want to look at it, not with your level of comfort doing something because your experience is different than everybody else. I always model it after that. Think about someone you really care about who has no knowledge or experience of safety, electrical, anything, maintenance, and then picture them standing in there because that may be that case for a person that's in that machine. So like I said, risk assessments, people are always scared. We don't want to do it because they think there's like it's complicated or there's some major liability if they guess wrong. What it really comes down to is all the standards, and they're all the same. They look at 3 things. How badly could you get hurt? How frequently are you exposed to that hazard? And then is it possible to avoid it? So if something happens, can you even get away from it? Is it a robot that moves so fast you don't even see it coming? It's just going to whack you. Um, so really, if you can answer those 3 questions, and again, get a team of people and everyone comes to a consensus, you answer those questions, this chart on the right, you follow it. So, okay, it's minor. Okay, I pinched my finger, got a Band-Aid, I got an ice pack, and I'm back doing my job. To, moderate, I broke my arm, but I can fix it, right? I can wear a cast. I'm out of work for a while. Then you get to serious, which is it's an amputation. It's crushing. It's death. So that's what you answer first, which those are pretty easy for most people to think about. And then exposure to the hazard. So you completely box it in, right? You can't get to it. Well, that's prevented. That's the lowest level. Low exposure, more than once an hour. So again, a lot of people think, well, we don't get in there very often. I ask them how often they get there. Oh, every 15 minutes. Well, that's considered quite a bit for safety. You're exposed to that quite frequently. High, less than once per shift. So it follow the chart through. Avoidance of the hazard there too is, if I hear it moving or I can see it because it's moving slowly. There's nothing I'm not going to get pinched between it and a fence or anything else. Can I avoid it? So there again, you answer those. Yes, it's slow. It's less than 10 inches per second, which is a standard that says that's avoidable. So you don't have to even consider it a hazard necessarily. To again, it's moving so fast, or it's because of the clearances. I had to crawl inside this confined space, and if something happened, I just couldn't get out in time. So answer those questions. You work your way over from left to right, and you'll get to your risk level. So again, you don't have to be a scientist, you don't have to be an engineer, you don't have to be a safety expert, specialist, whatever. Just about any person you grab off the street can look at something and answer these 3 questions, and it's valid. You'll get a valid response. That's again, build that team, come to a consensus that everyone feels is good and move on with that. So the other thing we get to is, well, what exactly is this serious, moderate, minor? So in the standards, they do specifically say examples. So minor, bruising, small cuts, no loss of time. Um, I always love this moderate fingertip amputation, but not a thumb. A thumb amputation is a serious. Apparently, thumbs are much more valuable than a finger. But so there again, you don't have. If someone questions that, well, gee, I just don't know. There are in the standards charts that will tell you specifically, and this is a very small sampling. When you get into those, there's under minor, there's probably 300 things, and under moderate, there's even more. So again, you don't have to make it up. Like I said again, I would always rely on standards. Again, risk scoring, prevented, high, low, again, very well defined, gives you much more detail. Well, we put a gate, interlock guard in front of it. Is that prevented? You don't know. It tells you right here. Yep, it's interlocked. So, and then avoidance of the hazard again. Well, I don't know what speed it moves or what's avoidable or things like that. Again, standards point that out. So I highly recommend all of this is in there. You don't have to recreate it yourself. So to me, the thing that most people try to avoid is doing the risk assessment because they think it's scary. And I honestly think of the whole process, it's the easiest thing to do. Identifying the task hazard pairs is the hardest because we do a seminar where we actually do hands-on and we sit it down, we put here's the machine and we'll have 40 people in the room. Every one of them will come up with a different number of tasks. Usually it's 5 to 10, and then we tell them, well, there's actually 43, and they about flip out of their chairs. It's because you got to think of so many little things that seem common sense, but you still have to account for them. So again, identifying the task hazard pair is much harder than actually rating what the risk level is. And then if you ever hear there's different ways to categorize risk, there's performance level, which we tend to use more in machine safety. So C, A, B, C, D, and E, obviously E is the highest, A is the lowest. They move up from there. And then the other one you might hear is SIL, S-I-L. So SIL is a standard a lot of Europeans, the ISOs use. And also, but there's two SILs. So there's SIL and machine safety. So in machine safety, we are concerned about hurting one person. That's the way we look at it. Our concern is no one gets hurt at all, period. When you get to process safety, which also uses SIL, it's where it gets confusing. So process safety, refineries, chemical plants, things like that, where they're doing huge batch processes, they look at safety in a different way. In their world, it's okay to kill people. Not that it's okay to kill people, but they assume we have an accident, people are going to die. So their safety process is how do we minimize that? How do we keep instead of a town being, 2,000 people dying, we will sacrifice 10 people to save the 2,000. So that's where a lot of people get confused on SIL. SIL applies in both. They mean totally different things depending on which standard you're reading. So in America, we tend to go more with performance level. That's your ANSI standards and your 13849 standards. So we'll do performance level. Again, other ways to do it. The 13849, again, you're still answering those same three questions. Severity of harm, S1. What happens, how serious, or how often you're exposed to it, and then can you get away from it? So the SF and P are all those. When you get to risk reduction, now you figured out what your risk is. How do I get rid of it? Well, they have ANSI B11.19 is probably the most referenced one, I would say, in America for sure. And that one is going to give you all these things. Safe distance, I have light curtains. Where do I put them? I don't know. There's a calculation for safe distance. Okay, there's a fence, but someone could reach over it. How do I know how far they can reach? There's a chart that shows you that. How high or low does my fence need to be? How does my guard need to be designed? Can I put a finger or my arm or my whole up to my shoulder through it? That's all defined in there. So once you figure out what you're doing, it's easy to find this kind of information so you're not the one trying to figure all that out. So as we go through risk reduction measures, we want to answer questions. Is it inherently safe by design? Usually if we're talking about machine safety, it's not. There's something that can hurt someone. And so again, you'll just kind of follow your flow chart around and do all the different things. And the idea is to get back to that point where you answer, that question that we've fixed the problem. We reevaluate the task after we did all these measures, and now we are confident it's safe. So it's just a process. And again, once you get in the flow of doing this process and repeating it, it just becomes second nature. It's very easy to do. We also have what they define hierarchy of control. So again, I said you could put a sticker on it, or you could have sit everyone down in a room and say, "Don't do this." That's what we call an administrative control, and you can see that's all the way down at the bottom. So that's the least effective because it relies on a person doing something by their own choice. They have free will. That's what you're relying on, not the most reliable. Above that would be engineering controls. So again, now we're going to put sophisticated systems in place to take a lot of that risk out. So even if people try to do something wrong or they make a bad decision, they're covered. It's going to catch it for them. Or you get up to the inherently safe by design. Again, we always say first try to design it out. Can we get the person away from it? Can we put a robot in? Do we really have to do that task while the machine's running? Which is obviously the best. If you cannot have the person in that machine, that's the best solution, but not always possible. People always get scared of this. So here again, a safe distance calculation, again, in the standards. So things you have to consider. K is how fast someone's moving. You see all the T's in there. So that's people don't think about this. So I hit an E-stop. That triggers a safety relay. The safety relay tells a motor starter to turn off, and then the motor stops. All of those processes take time. So you have to add up all those times. It's usually milliseconds, but it makes a big difference. And that will affect how far away you have to detect a person coming into a safety situation. And then the DPF, depth of penetration, that's am I worried about their finger or their hand or their whole body? So there's different, obviously, if you're trying to protect against a finger, you got to stop faster because the finger's small and it can go. And so you got to really have a small device that can pick that up versus a whole body. But if you're just detecting a whole body, you might have to be way far away because they can reach out with their arm and lean forward before they even trip the device to detect that they were there. Nice thing too, in the standards, water stopping at times. Um, how fast do people walk? Those are in the standards. How fast can someone reach their hand out? That's in the standards. We haven't defined. Generally, most standards are going to be around 2 meters per second moving speed for a human walking. So that's kind of what you stick with as a basis. But there's ways to go one way or the other. It's confined space. They can't move as fast. They're wearing something that restrains them. So again, it's all in the standards. It's just an example of a reach over. Again, gives you here's what you have to consider. Someone can go over it or around it, under it or through it. So it gives you all those distances. This would be for a hard guard, same thing. Here, fingertip, how big's the opening size? What can it be? The shape of it. Finger up to the knuckle, whole hand, and they like I said, they'll go arm to the elbow, arm to the shoulder, all that kind of stuff. Anybody have questions so far? Keep going.
Yep,
So
I
when
don't
we
see
talk about
anything coming up there. Yep.
okay,
So, yep,
so
go.
we'll talk about performance levels. So all that risk assessment did when we went through all that was it gave us what we call PLR, performance level required. So in that safety circle, when you look at that, we said we're going to do a risk assessment. That's going to tell us how dangerous the risk is. So from that point on, everything we do, the functional spec, the design, everything else is going to be based to make sure that we get to that performance level. Because if we determine it's a PLD, but we only designed a PLC, it's not safe. Now, if it's a D and you design to E, you're fine. You can always go higher, but you can never go lower. And again, the risk scoring system, this is kind of what we went through before, severity injury, how often are you exposed, and can you avoid it? And that's why I always tell people, I answer those 3 questions, and I repeat it all the time. What's it going to do to you? How often could it do it to you? And could you even get away from it? So answer those, and you're going to be able to get your risk level. So there's 2 components to it based on risk, performance level, and then what they call structure category. So in the old days, we did everything with one wire. And then we had a lot of safety. I'll ask people what their safety standards, and they say, oh, we're Cat 3 here, category 3. So that was kind of an older thing that came about where we first figured out, well, gee, if there's one wire is good, aren't two wires better? Because in the world of safety, redundancy isn't one plus one equals two. It's one plus one equals a million. So we're worried about not something failing in a way that it shuts the machine down. We're worried about something fails and the machine still runs and you don't know it failed. So that's where adding that redundancy is, and that checking and all the other things we do takes that, it goes from, one incident takes it out to now you have to have two distinct incidents take it out. And the likelihood of that happening with good quality equipment to both at the same time, and you don't know one of them failed, is very low. And so again, that's where one plus one equals a million or more. So when we have these structures, category two, category three, category four, that's what they're talking about. It's the physical design of the circuit. So the D, the E, the C's, those are how good the equipment is. That's the quality of the equipment. How reliable is it? This is going to go 10 million cycles. It's going to 100 million cycles before it fails dangerously. The category structure is I have one of them or I have two of them. Difference between category three and four. Three is I have two of them and I check them. So I have a contactor that has an aux contact. I tell it to close and I send that aux contact feedback back to my safety system. And it says, yep, I told it to close and it closed. So it's monitoring that. But the safety system, that circuit itself, the monitoring circuit, doesn't have to be a safety input. It can go to a standard input in your logic, because if it fails, the device detects it and it kicks out. So it'll tolerate one failure. Um, on a Cat 4, it doesn't let you tolerate any failures. It has to know the failure happens before you ever had a demand on the safety cycle. So with a Cat 3 structure, you might not know of a failure until you hit the e-stop. Now you have two, so it will still shut down, but it's going to say, well, gee, that one didn't work the way it was supposed to. I'm not going to let you turn the machine back on until you fix it. And a category 4 structure, it's actually doing pulse testing, complementary testing. It's testing those monitoring channels all the time. So it knows the instant a failure happens and shuts down the machine. It doesn't wait until someone has, breaks the light curtain or steps on a safety mat. It will the machine's that seriously dangerous. We have to shut it down. So as soon as it detects that failure, it will turn the machine off. It doesn't wait for someone to do something to tell it to stop. Um, the world I inhabit most, I would say 99% of what I do is the category D or performance level D, category three. And the nice thing about that is all of the good quality safety devices nowadays will get you to category three, performance level D easily. All of them will. It's very easy to achieve that. Um, if you have an E hazard with a structure, category four structure, one, those are expensive devices and it's really tricky to do it. Because you're limited on what your choices are. You're limited on your input devices, your logic devices, and your outputs. So I usually tell people when we arrive at it, because I've had assessments where we got to E's, and like, what do we do? And I said, you go back to step one, you design it out. What can we change? Either make sure a person's not in there. Okay, it's too dangerous for a person, put a robot in there. Let them handle that. Get them out of the equation. If we can't do that, well, let's do something that changes how they interact with the machine so we can get it down to that D level. It's not an absolute going to kill you. It just may hurt you, but probably not. So there again, E's are really hard and they're very expensive. They tend to be more finicky, so you're going to have more nuisance trips because again, it's always going to err on the side of caution. Because for us in machine safety, it's not that we don't care about production or we don't care about damaging the machine, but our first and only concern really is that person. Yes, we will let a machine destroy itself or a process, lose $1 million, but it didn't hurt a person. That's kind of the mentality you have to have. So, and when we come to performance level, so I talked about calculations and things. So all of these things have numbers. How do we know how good a safety device is? There's calculations we do, and they're quite large. It's all algebra, but they're huge equations that scare people, even though it's just algebra, plugging numbers in. But we concern about things. So MTTFD, that's mean time to failure dangerous. And I always get this with drives. So we calculate out the MTTFD on a PowerFlex 753 drive. It's 63 years. And I have people say, well, I've never had a drive. A drive won't last 63 years. It's like, well, I don't care if the drive fails normally. If the drive fails normally, it turns the motor off. That's the safe state. What I'm concerned with is the drive failed in such a way that I don't know it failed. And when I tell it to stop, it doesn't. So when we say it's dangerous failure, I don't care if it stops working. If it's a contactor and it burns up, that's fine. The motor stopped. So we're only concerned with when it fails a way that allows the hazard to still operate, and we don't have any clue that it failed. So um, how we look at that, one channel, two channel design, circuit design, again, category. We're concerned with that. Affects how reliable it is. DC is diagnostic coverage. That's the monitoring feedback I was talking about. Is it good? Is it a directly linked contact? If you see the red contactor versus the regular one, literally the same device, other than the aux contacts, and are tied directly to those movable contacts physically. There's no springs, nothing else. So if the main contacts are made and power is energized, that contact absolutely is made, or so it opens and closes with it. We're guaranteed. E-stop's the same way. On an emergency stop, you have to have that mechanically linked contact, so we know that it's actually stopping. It's following what you're telling it to do. And then common cause failure is the other thing. So in safety, it's pretty neat. We like redundancy. If you have something that has a computer processor in it, we're going to have two, and they're going to be different. So here again, think about that. If you're a programmer, you have to program a whole set of code for one chip and a whole set of code for a different chip, because the one thing we don't want to do is use the same two chips. The manufacturer missed something, or they made a mistake, and now you've got the same failure mode of failure in both of those chips. That's not good. So they will use different things. That's quite common in the higher end devices. They will have sometimes they even have four or six just to help eliminate that, make them safer. So again, when we talk about performance level, and we got those other charts, that kind of told us, the low, medium, high, we can go in here, and this shows you the performance level and category relationship. So I know I want a performance level D, but what category I need? Well, I need to be out here. I'm Cat 3. I'm good for 24 years. That means I'm greater than 24 years. Every device in that system will last at least 24 years before it fails dangerously. And this is why I say most people go D3. So in the standards, the thing people don't like is if something's 20 years old, you throw it away. It might work, it might be fine. It could work another 100 years, but we just assume it's lived its life and we pitch it. So again, if you have an older machine sitting out there, that's one thing to ask yourself. How long have those safety devices been in place? If it's been greater than 20 years, we don't consider them safe anymore. They have to be replaced. And again, when you come over here, performance level D, that's 1 in 1 million. So what they're saying is there's a 1 in 1 million chance that in any given hour, that system could fail in a dangerous mode. So that's why, D is good. E is better because that's a 1 in 10 million chance. So go back to the Dumb and Dumber. So you're saying there's a chance. That's what we're talking about. So again, this is where I say 1 + 1 = 1,000,000. That's what I'm talking about. So D, Cat 3, it's really 1 + 1 = 1,000,000. So here we go. The other thing too. Okay, so now I figured all this out. How do I know what to use? So if you're using electronic stuff, it's really easy. They print it on the label, tells you what it is. You look at the side of a safety relay and it'll tell you this is good for performance level E category 4. It'll tell you right on there. A VFD will do the same. So a system, the manufacturer made it and they've actually tested it and they've determined those values and they print it right on you. They put the stamp on the box so you know. Makes it very easy. The trouble is when you get into an electromechanical device. So electronics fail based on time. That's when they'll fail. That's why they can do all those testing and calculations. An electromechanical device, a contactor, a safety switch, e-stop, gate switch, things like that, they're going to fail based on how often you use them. So if you push it, once a year, it's going to probably last longer than if you push it, 200 times a day. Because every time you operate it, you're losing life on that device. So the trick there is we kind of have to know how often it could get operated. And again, we go through other calculations. So to do that, manufacturers will publish data that MTTFD, mean time to failure dangerous, it's called the B10D. They'll put that out there and you have to enter that into your calculation. This is why I talked about the big calculation you do. These are all those numbers that you see under the electromechanical that you need to know. You do the calculation and then you go to the table K in ISO 13849 and it'll tell you, okay, here's what you calculated, here's what it equals. So this is your performance level right here. So then we have to take everything we have in the system and add them all together. and there's a calculation for that. So I've got some contactors, I've got a light curtain, I've got an e-stop, I've got safety relay or safety PLC, and there's calculation to figure that out. So you add these all together, and then that is going to verify that yes, we did our safety function. It meets per this table. We meet what we said we were going to do. So we had a required PLR that was PLD. We just did all these calculations, and we find out on the turn it says, "Yep, you're PLD. You're good to go at that point." Nice thing is you don't have to do all these calculations yourself. There's a software that's out there. It's free. It's called Systema. If anyone's ever seen it, it's German. TV put it out. Free software you can download, and it will actually you enter all your system data in and what your performance level required is, and it does all the calculations and spits you out a nice little document that says, "Here's what you told us you needed to be at. Here's what you're putting in the system. We did the numbers, and yes, you meet it, or no, you don't. If it says no, you don't, you go change it and fix the problem." So I was talking about kind of that armor. That's another thing that's an armor. You do that calculation, you print off the documentation, you put that in a file. If something ever happens, you get that file out, and it's one proof you did your diligence, proof you did the best you could, and then it also gives you that point to start. Well, what did we miss? And you can kind of look back through it. So that's just an example of a safety system. So, safety function, we call them. It's an input device of some kind. Here, it's light curtain. Something has to make a decision based on those inputs. That's your logic device. Could be a safety relay or a safety PLC. And then we have an output device, contactor in this case. And you can see the PFHDs now, the first two, those would have been printed on the side of the box for the light curtain and the logic. The output contactors, that we're going to have to know a number of operations and do all those calculations, and then go to table K, and it's going to tell you what that means. Then we add all those together, and that right there you can see that's 1 in a million. So that this system here would be good for PLD Cat 3. Nice thing too, when I talked about harmonization, so there's two ways to do it: performance level or SIL. Like I said, in America, we're typically performance level. Europe's more SIL based. But if you look at the numbers, they're the same. So if you go to the highest PLE, it's the same as SIL 3, which is the highest there. If you look at PLD, it's the same as SIL 2. So they do add up. And that way, people say, well, here I did everything in it. I got a PLD, but now I have to ship it to Europe and they want a SIL. I got to redo all the calculations. No, since the standards are harmonized now, you can reference this and say, well, we did everything to PLD and that meets SIL 2. And people accept that. It's perfectly valid to do that. You don't have to redo everything. And 1 in a million. I think that's all I got on that. Does anyone have any particular questions or anything that you want to know that I didn't go over? I tried not to get too deep into it, but
Yeah, if anyone has the participants, attendees have a question, if you want to raise your hand, I could unmute you and you could speak. Oh, there we are. Okay, Adam.
Okay, thank you for your time. This is a great presentation.
yeah.
Um, I've been a controls engineer pretty much since getting out of school, so maybe for like 10 years or so.
Mhm.
And like I always work on the after product of the specs and all the meetings. I've never been really involved
Invited
in
in.
looking at specs and studying them.
Yeah.
So what would you recommend to kind of get into more of it, kind of get to that next level, or even like it's all online and available for free, or at least a lot of them are, I know. What would you recommend to just access more and really get involved with them more?
Yeah, if you want to become I'll tell you the steps I kind of went through. So when I started with Square D, they didn't even have safety relays at the time. Those came out about the turn of the century, was when well, I guess Europe had it in probably 95, 96. So I remember in the early 2000s when these safety relays showed up in America, and everyone's like, well, what the heck are these? And why would I have to use that? I got my e-stop one wire and my master control relay. So you kind of had to self teach, and you just got it through experience. This guy told you how they did it, and you kind of went through it. What's really nice is TUV came out probably, I would say, 10 years ago with a program that you can get TUV certified. So TUV actually is the one that created a lot of these standards, the machine functional safety standards, and they have classes you can take and you can get certified. So there's three different levels. One is the technician level. That's basically a 2-day class. You go in, it touches on a lot of the stuff I talked about. It goes through more detail, obviously, on the calculations, picking equipment. You really dig in more to that mechanical operation thing and learning how that affects what you do. And at the end of it, you take a test, and if you pass, now you're a TV tech, is what they call it. And that kind of leads to the next step, which is where I am. I'm an engineer. So the engineer is a little more detailed. It's a week-long course, and then you take 6 months off to study the standards, and then you come back for another week-long course, and you take a 5.5 hour test. Um, it's not that the test wasn't horrible. It was 5.5 hours, so couldn't be great. But yeah, it wasn't bad. But that's what you go through to be that engineer. At that point, you really have a really good understanding of it, all aspects of it. Like I said, it's standards based. It's really getting to know those standards. And by the way, it's an open standard test. You can take them all in with you. But so that's a little more serious, a lot more time commitment, obviously. And then the very next level is what I'm being prompted to do. Not that I want to, but they have what they call a functional safety expert. So that you have to have had at least 5 years as a safety engineer, as a engineering level. And then you basically have had to you submit a design that you did from beginning to end, like a whole project, to a board in Germany. And then they get about 5 or 6 really, really smart engineers who will grill you for 3 or 4 hours about that project. And if they, which is really fun. We had a guy that I worked with that did it, and man, he came out sweating bullets. But they dig in, and if they at that point say, "Yep, we think you know enough," then you're golden. You have that forever. It's a thing. So that was one way to get into it. And so my company, Van Meter, we host those a lot. Rockwell Automation, most Rockwell Automation distributors do. So no matter where you are in the country, it's really available. I know we have them quite often. We do both levels. So we do the first two, the tech and the engineer. So that's a way to do it. There are a couple other companies out there doing a similar thing. They kind of just copied the TUV system and they're out there, so it is available. So there are some online ones that you can do. I really think it's worth sitting down in a class with someone that really understands it, though. It was valuable for me. You get a lot better discussions. But the biggest thing is, I always tell people, is just get involved. Like I said, if you know there's a new machine coming in and there's going to be a thing, ask to be a part of that risk assessment group of people. Because again, you have to take what they said you need. You have to create this. I have to make it work now, right? You may have questions that you're doing things maybe they didn't think about because you know what it really means doing controls, picking out hardware, wiring it up. How does this affect things? So there again, reach out. I've had a lot of involvement with EH&S people now. They're getting highly involved with machine safety. We do a lot of seminars with them because they're like, we speak safety like trip and fall, harnesses, earplugs. That's what they think of as safety. When they look at this world, they don't know what any of this stuff is. And they're like, we don't know how to talk to these engineers about machine safety. So I do a whole presentation just for EH&S people to get them down this path. And because I said they should be in that room, right? This is safety. It's under their bucket. They're responsible. And what I always tell the engineers and designers and controls people is like, you want those people in the room because I got to tell you, their budget's bigger than yours. So if the H&S person says we have to do this, it's amazing how that greases the wheels to get moving forward. So yeah, I would say that if you know there's people that do it, just ask, hey, next time you have a project, can I be involved? It shouldn't be a problem. And that's just kind of how you get into it. No, go back 5, 6, 7 years, no one was an expert at how to do this. Rockwell teamed with TV to really make an effort on how do we do this better? How do we educate people? And it's exploded. I think right now, there's probably, last time I looked, you'll actually be listed then if you get a tech or an engineer or an expert that you're listed on TV's website, so you can look it up. If you have my number, that's on my emails or my cards, you can type that in and see my credentials. But last time I looked, there were about 400 TV engineers in the United States. There were several thousand techs, experts in the world. So I think there's only maybe 10 or 15 in the United States, and there's probably only two in the world. So it's a good thing to get into. And the thing I like about it is I look at stuff so differently now. I've been doing this a long time, and things I never thought about that just now to me seem like so common sense. Gee, why are we doing that? It's so easy to protect against that. And unfortunately, like I said, I get a lot of phone calls where customer says, "Hey, can you get over here? How fast can you get over here?" And they won't tell me what's going on. That tells me they had an incident because they don't want to talk about it till you're on site, till you're there in person.
Mm,
And those are the worst
mm,
calls to get. And you get over there, and I have to say, to this day, I've only seen one or two that was like, you never could have guessed that. Yeah, it just came out of nowhere. I don't care how long you talked about it, how many people looked at it, no one would have thought that was possible to happen. Most of them are like, man, that would have been just someone asked one more question. It would just been that easy. So I always talk about culture and safety. So there again, if you're a controls guy and you get passionate about safety, talk to people about it. Ask people how to get involved. That's why I say the more you talk about it, the more you get more people thinking that way, the easier it is. And again, the whole idea of safety isn't to mess with anybody. It's not to screw with people. It's not to make their job harder. It's the message you want to say is from the top to the bottom. Everyone in this plant wants everyone to go home every night. No one wants to make the phone call to, a spouse, a child, a parent to say, hey, something happened. Like I
mhm.
said, I've been at plants that have had that. It's horrible, and it will affect forever. So
Yeah,
it's
and
good to
I
be
had a
passionate
saying.
about
yeah,
it.
we got one more question here. If
I,
that
Okay.
we'll just run out of time. I hate to cut you off, but um, I'll Daniel, you had a question.
Yeah, Matt, can you hear me?
Yes. Yep.
Excellent, great presentation, very nicely
Oh, thank you.
defined. I have a question for you. I'm doing a design right now, just for an internal project, and I'm limited to a conduit, only one conduit for sending control signals to and from a machine and its controller.
Hmm.
And so I'm running redundant signal paths, but they're going through the same one conduit. If something's going to happen, it is sort of a life safety function. Bad things could happen. Certainly, expensive things could happen if both circuits were to disappear. What I'm thinking that the fallback would be some sort of a wireless connection. I don't like wireless. I don't think it's reliable. But what do you recommend in sort of just that
Well,
broad strokes?
again, as far as the personnel safety, whether it happens to one or both, the machine still stops. So that
Well,
that case, what I guess the worst case would be, you're concerned if it happens to one and you don't know what happened to one. I would say it's pretty common. Most people use like they'll run a cable, so both of our safety signals are in the same cable. That's pretty common. But again, they're monitored because we do pulse testing, different things because people are like,
right,
well, if the wire gets cut, we know it gets cut. Well, what if it gets shorted? If it's a normally closed contact, it gets shorted. They crush, not that they crush
right.
conduits, but they do. We do pulse testing. It can detect that. There's ways that the newer, higher quality electronics detect a shorted wire and things like that. So, yeah, it's fine to run them in the same thing because again, if there's a failure, it fails in the safe mode. It's going to stop.
Well, no, no,
Uh,
no. Stop would be a fatal mode. The
that'd be the
machine
bad
has,
thing.
yeah, that'd be a bad thing. So the machine has to keep running. If it keeps running, that is probably much less dangerous. It can be worked around until a place where the machine can stop safely is okay. So that's my dilemma. Is that I need to, that's why I'm thinking of going to the wireless because I want to maintain control, not so much for
Well, and
non-safety reasons.
there is wireless safety. They do have that, and it
Really?
operates with multiple channels, different radios, things like that. So there is wireless safety.
Hmm.
It's a valid thing. Biggest thing you just have to pick the right frequencies and the right type of wireless for your environment because
Mhm.
some environments are just not. If you have a lot of welders, certain
Right.
frequencies don't work well. But there is wireless safety out there quite a bit. That's
Okay.
that's pretty well defined. I mean, there
So
are standards again that have defined safety radios and things like that.
interesting. Okay, great. So I guess it's considered a useful workaround. Thanks. That's all. I did have a couple of questions.
Yeah,
The what was that? Not the Sistema website. No, I guess. Oh yeah,
yeah,
robots. You've been talking
yep.
about robots. It's coming up. You know, Tesla is working on their humanoid robots for factory use.
Mhm,
And I'm imagining that the trying to define the machine safety for an autonomous robot,
mhm.
I can't even imagine how you make that stick in a court of law. because it's autonomous, right? It can roam around doing whatever it's doing.
They are in a way. They still have a defined operating system. So, my company, we don't sell like the big robots, but we
Right.
sell cobots. So the whole idea of a cobot is the way it's designed, it can't really hurt you. It moves slow enough, it doesn't have enough force, it can sense when it makes contact. So you can collaborate with it. And that's, I'm assuming, what they'll do. There'll be limited amount of power in those robots. They won't move fast. They'll have, again, sensors in them. So if they make contact with the person, they would stop. So that, yeah, that's kind of how they do that. It's just inherent safety in the
Oh, I see.
design of the machine. Because they do, even though we say they're autonomous, it just means they're still operating by a defined code. It's just no one's directly telling them what to do. So
Well,
that's
how
what
about
when they say. But we've had autonomous robots, large things. John Deere has one that pulls 38,000 pounds around their factory. There's not a person on it. It just does what it does. And that one could really hurt you. It can, like I said, it pulls 38,000 pounds all over that plant, and there's no one operating it.
So is there specific standards then? This is Ken
Oh yeah,
Cole. Is there specific
yep,
standards that go along with autonomous robots,
yep,
or
yep.
because they've
That'd
been
be
around
the yeah.
for enough time, I would think that we're not skating ahead of the standard at this point.
No, yeah, no, there's very well defined, and they're defined not only for the physical part of it, but in the coding. So there is safety coding too, requirements on how you code safely and redundantly and properly, so that you don't have glitches that would cause a safety incident. But yeah, autonomous robot specs have been around since the geez, probably early 2000s. So again, that's that, in ANSI, you drill down to a type C spec. There's ones for AGVs, automatic guided vehicles, totally autonomous robots. Yeah, that's the nice thing about standards. You can just about anything that's out there, someone's already thought about it and they put it in that standard. So yeah, I wouldn't be too afraid. I'm more afraid of them deciding they don't want to listen to us. But
what's the safety standard on that one? So what is that if I'm involved in programming a humanoid type robot in some future year here, what standards should I be looking for to look? Where do I read this stuff of what guidelines for programming? That's I think what I need to.
well, that's going to be within those ANSI standards or the
Okay.
IEC standards. So yeah, you just have to drill down until you find the one that tells you how to do that. So in my world, we use safety PLCs. So
Mhm.
within ANSI B11, there's a whole section on, how you do safety in a PLC. Very specific. And it's not just physical, how it's made and built and how you connect it, but it's also, yes, in your code, you have to do these things in this specific way. So yeah, there'll be standards out there for that that'll tell you this is
Great.
exactly what you can do and what you can't do. So
Thanks, Matt.
yep.
Lots of information.
And I can forward this presentation to Ken if you guys want it.
Yeah, sure. That'd be great.
Okay.
We'll be able to get that into a site somewhere. Be super.
Cool.
Okay.
Appreciate the opportunity to talk with you guys.
You have any other questions? All right. Thank you very much for attending. And hope to be able to see you at the next IEEE presentation.